Causes of piping vibration, understanding factors contributing to vibration in pipelines. Piping vibration, causes and mechanisms. Piping vibration refers to the dynamic oscillatory movement of piping systems caused by internal or external excitation forces. Although vibration amplitudes may appear small and sometimes imperceptible to the naked eye, their long-term effects can be severe and destructive. In industrial facilities such as oil and gas plants, power generation units, chemical plants, and refineries, piping vibration is one of the most common contributors to fatigue-related failures. Understanding the causes and mechanisms of piping vibration is therefore a critical competency for engineers involved in design, operation, inspection, and maintenance. From a mechanical integrity perspective, piping systems are designed primarily for pressure containment and thermal expansion. However, they are also dynamic structures that respond to excitation forces. These forces may originate from fluid flow, rotating equipment, pressure pulsations, acoustic energy, or even external environmental influences. When the excitation energy interacts with the structural characteristics of the piping, such as mass, stiffness, and damping, vibration can occur. This presentation focuses specifically on the causes of piping vibration rather than measurement or mitigation. By clearly understanding why vibration occurs, engineers can more effectively prevent it through proper design, detect it during operation, and manage it during inspection and maintenance activities. The discussion will emphasize practical, industry-relevant mechanisms that are frequently observed in operating facilities. In addition, this presentation adopts a structured approach by grouping vibration causes into flow-induced, mechanical-induced, and structural or design-related categories. This framework helps engineers systematically analyze vibration problems instead of relying on trial-and-error solutions. Ultimately, understanding piping vibration at a fundamental level supports safer operations, improved equipment reliability, reduced maintenance costs, and longer asset life. The agenda outlines the logical flow of the presentation and sets expectations for the audience. It begins with a clear definition of piping vibration to establish a common technical understanding among participants. This is followed by a discussion on why piping vibration is a critical issue in industrial facilities, particularly from safety, reliability, and integrity perspectives. Next, the presentation introduces the main categories of piping vibration causes. This classification is important because vibration problems are often complex and multifactorial. By grouping causes into flow-induced, mechanical-induced, and structural or design-related sources, engineers can more easily narrow down potential contributors during troubleshooting or design reviews. The agenda then moves into detailed explanations of specific vibration mechanisms, such as turbulence-induced vibration, flow-induced pulsation, acoustic-induced vibration, and vibration transmitted from rotating equipment. Each mechanism is explained in terms of how excitation forces are generated and how they interact with the piping system. Following the technical discussion, the presentation highlights typical industry failure examples that have been directly linked to piping vibration. These examples help bridge theory and practice, showing how vibration manifests in real operating environments. Finally, the presentation concludes with key takeaways that summarize the most important learning points and reinforce the need for proactive vibration management throughout the asset lifecycle. This structured agenda ensures a comprehensive yet practical understanding of piping vibration causes. What is piping vibration? Why piping vibration is critical? Piping vibration is defined as the oscillatory motion of a piping system around its equilibrium position due to dynamic forces. These oscillations may occur in one or multiple directions and can be continuous, intermittent, or transient in nature. Unlike static loads such as pressure or weight, vibration is a dynamic phenomenon that involves time-dependent forces and responses. In practical terms, piping vibration occurs when excitation forces act on a pipe and cause it to move repeatedly. These forces may come from internal fluid flow, pressure fluctuations, mechanical equipment, or external sources. The response of the pipe depends on its mechanical properties, including stiffness, mass distribution, boundary conditions, and damping. Even a well-designed piping system can experience vibration if excitation forces are underestimated or if operating conditions change. It is important to note that vibration is not inherently abnormal. All piping systems experience some level of vibration during normal operation. The problem arises when vibration levels become excessive or when the vibration frequency coincides with the natural frequency of the piping system, leading to resonance. Under such conditions, stress levels can increase significantly, accelerating fatigue damage. Engineers must therefore distinguish between acceptable background vibration and harmful vibration that poses a risk to integrity. This distinction requires both an understanding of vibration mechanisms and awareness of industry guidelines. Recognizing piping vibration as a dynamic interaction between excitation and structural response is the foundation for effective prevention and control. Piping vibration is a critical issue because it is a leading cause of fatigue-related failures in industrial piping systems. Fatigue occurs when cyclic stresses, even if relatively low in magnitude, are applied repeatedly over time. Vibration produces exactly this type of cyclic loading, often at high frequencies, which can rapidly initiate and propagate cracks. One of the most serious consequences of uncontrolled piping vibration is loss of containment. Cracks caused by vibration fatigue may lead to leaks of hazardous fluids, flammable gases, or high-pressure steam. Such events pose significant safety risks to personnel, can result in fires or explosions, and may cause environmental damage. From a regulatory standpoint, vibration-related failures can also lead to compliance issues and penalties. In addition to safety concerns, piping vibration affects reliability and availability. Vibrating pipes can damage supports, loosen bolted connections, and transmit vibration to connected equipment. This can result in unplanned shutdowns, increased maintenance costs, and reduced production efficiency. From an asset integrity perspective, vibration problems are often difficult to detect visually until damage has already occurred. This makes early identification and understanding of vibration causes especially important. By addressing vibration proactively, organizations can significantly reduce risk, extend equipment life, and improve overall operational performance. Main categories of causes: flow-induced vibration, FIV. The causes of piping vibration can be broadly classified into three main categories: flow-induced vibration, mechanical-induced vibration, and structural or design-related factors. This classification provides a practical framework for understanding and troubleshooting vibration problems in the field. Flow-induced vibration originates from the interaction between the flowing fluid and the pipe wall. This category includes mechanisms such as turbulence, pressure pulsation, and acoustic excitation. Flow-induced vibration is particularly common in high-velocity systems, gas services, and piping connected to control or relief valves. Mechanical-induced vibration is caused by dynamic forces transmitted from rotating or reciprocating equipment such as pumps, compressors, turbines, and motors. Issues such as imbalance, misalignment, looseness, or cavitation can generate vibration that propagates into the connected piping. Structural or design-related factors do not generate vibration by themselves but can significantly amplify it. Examples include insufficient pipe supports, poor routing, long unsupported spans, and resonance conditions. In many cases, severe vibration occurs due to a combination of excitation forces and unfavorable structural characteristics. By categorizing vibration causes in this way, engineers can systematically assess potential sources rather than relying on assumptions. This structured approach improves diagnostic accuracy and supports more effective corrective actions. Flow-induced vibration is one of the most common sources of piping vibration in process industries. It occurs when the kinetic energy of the flowing fluid is converted into fluctuating forces acting on the pipe wall. These forces can excite the pipe and cause it to vibrate. The likelihood of flow-induced vibration increases with higher flow velocities, changes in flow direction, and disturbed flow conditions. Components such as elbows, T's, reducers, valves, and orifice plates are particularly susceptible because they disrupt the flow and generate unsteady pressure fields. Flow-induced vibration can be either random or periodic in nature. Random excitation is typically associated with turbulent flow, while periodic excitation may result from pressure pulsations or vortex shedding. Both types can lead to fatigue damage if the resulting vibration levels are sufficiently high. Understanding flow-induced vibration is essential during both design and operation. During design, engineers must ensure that flow velocities are within acceptable limits and that piping stiffness is adequate. During operation, changes in process conditions, such as increased throughput or different fluid properties, can significantly alter vibration behavior. Effective management of flow-induced vibration requires awareness of where it is likely to occur and how it interacts with the piping system's dynamic characteristics. Turbulence, pulsation, and acoustic-induced vibration, mechanical and structural factors, failures, and key takeaways. Turbulence-induced vibration is caused by random pressure fluctuations generated by turbulent flow. These fluctuations apply continuously varying forces on the pipe wall, leading to broadband vibration. This mechanism is common downstream of flow disturbances such as elbows, control valves, and reducers, particularly at high flow velocities. Flow-induced pulsation, on the other hand, is characterized by periodic pressure fluctuations. It is commonly associated with reciprocating pumps and compressors, where the fluid is displaced in discrete volumes. Pulsation can excite piping at specific frequencies, increasing the risk of resonance and high vibration amplitudes. Acoustic-induced vibration is a high-frequency form of flow-induced vibration typically associated with gas systems. It occurs when high acoustic energy is generated by devices such as control valves, relief valves, or blowdown systems. Although the vibration amplitudes may be small, the resulting stress cycles are extremely high, leading to rapid fatigue failure. These mechanisms are particularly dangerous because damage can occur in a relatively short time. Small-bore connections and thin-walled pipes are especially vulnerable. Recognizing these vibration mechanisms and their typical locations is essential for effective inspection and risk management.